Okay, so as we mentioned, one of the main reasons to do modulation is to have high frequency signal. The reason for having high frequency signal because we need shorter wavelengths. So the antenna that we want to use to send and receive a signal for a longer distance, we need antenna. So to make a practical antenna, we need higher frequency transmission signal. But most of the signals which we have, like voice, they may not be high frequency. Voice is, for example, 300 hertz to the 3.4, or we just call it 4 kilohertz maximum. So if we want to measure or calculate the wavelength of voice signal is quite large. So you can't make an antenna such large, maybe in kilometers. So it's not practical. So therefore, we need to have high frequency. So we modulate messages or transmitting signals with a high frequency carrier, and then we can send by an antenna and we can receive by an antenna. So then the antenna can be a smaller size. So that is one of the main reasons. Then other than this, there are other advantages. So we can do multiplexing. If we want to send, let's say, multiple voice from the same channel, all of them have the same frequency, then they interfere to each other. So you can't separate them anymore. So it is like if all of you want to talk at the same time, so nobody can understand because they interfere together because they are in the same frequency. So, but if we have a carrier frequency, we can give each voice one carrier with a little bit different frequency difference, I mean. So then they can be sent from a channel. Later we can separate them by filter. So that is the advantages of modulation as well. Here I mentioned earlier, we may have different transmission. We may have a source in analog form. Then we send the analog signal by analog modulation. When we do analog modulation, we have band pass, means in higher frequency, in other words, or something which we need to filter them or after we did the filtering. So then this can go to receiver, do the demodulation and reach to the source, I mean the user. This is one way. Another way is we go to digital communication. We convert this analog to digital by doing analog to digital converter. Then this digital message or this digital data, which is in binary form, like 0101, converted to a signal, which we call it binary signal or digital baseband signal. Then we can modulate it and it becomes baseband signal or from a baseband channel, means there is no high carrier here. It's just become a signal. And maybe this signal we can send to from a channel. We receive in receiver side, which is we do demodulation, we convert it back to binary data, and that binary data convert to analog and sent to the user. Or we may do modulation using the binary data. We do bandpass modulation. So as we mentioned, like ASK, FSK, PSK, frequency shifting. So then we have bandpass channel, because now the signal is at a high frequency, we call it bandpass. Then at the receiver side, we have this digital demodulation, means convert back the modulated signal to binary data and then convert to analog and reach to the user. This is examples of possible modulation or transmission system. Yeah, and this was our demodulated system. We receive the signal at the receiver, do amplification, demodulation, and maybe another amplifier, and it goes to the speaker. Let's say this was a voice signal. Multiplexing, we mentioned, we have frequency division multiplexing, time division multiplexing, and code division multiplexing. Frequency division multiplexing can only be done if our signal is modulated with higher frequency. Otherwise, it's not possible. So that is one of the advantages we said we can have by modulation. Time division multiplexing can be done in both cases. It can be done for baseband signal and also for modulated signals. Code division multiplexing is same, can be in both cases, but usually we do for higher frequency, means modulation. After modulation, we do the multiplexing. So what they do is multiple channels. Here, the channels could be multiple voice channels, or could be multiple modulated channels. For example, few apartments in one area, they might be first the voices modulate with lower frequency, then later in maybe in few hundred meters, few of those combine together and make another multiplexing with higher frequencies, for example. In fact, we need to do modulation first, otherwise it's not possible. So what it's showing here is we do a multiplexing and we do a modulation as well after multiplexing. So in demultiplexing, similarly, we separate the channels. If it is frequency division, we need to have multiple filters. You need one filter for each user. And if it is time division, it's time division demultiplexer. Here is one example of time division multiplexing. So you can modulate or combine the signals based on time. So for each signal, we only take certain parts. For example, if you, for example, imaging, if each signal have, let's say, a certain period of time, let's say just as 1 second, just as example, each signal for 3 users. Each of them have 1 second of pulse duration. You only get sample 1/3 of a second. So means maybe you take one sample from channel 1, another sample from channel 2, another sample from channel 3, come back again to first channel. So, but this sampling will be quite fast, multiple times faster than the frequency of each channel. So, and that is minimum should be 2 times, but it will be usually much, much higher. So that is the concept of multiplexing. We will get them in detail later. In frequency multiplexing, frequency division multiplexing, let's say these 3 channels or 3 signals are our voice, baseband, analog signal, let's say is voice, they are same frequency. Each of them modulated with certain frequency. So first one with lower frequency, second one a little bit higher frequency, and the third one a little bit higher frequency. And then later they combine together and they will transmit. At the receiver, what we need to do, we need 3 filters based on their frequency, and then we should be able to get the original message. Yeah, this is about a short review of our previous class. Okay. The electromagnetic spectrum. So in fact, the spectrum is referred to all existing frequencies. Either we may say frequency or wavelength. The term of frequency and wavelength are the same, in fact. One is in terms of, the unit is hertz. Another one, the unit is meter. The difference is in some application we call frequency, in some application we call them wavelength. The reason is when the frequency become too large, then it's difficult to write them. Like for example, 10 power of 12, 10 power of 15, so hertz, for example. So that's in such large frequencies, easier to convert them to meters or wavelength. So then it becomes a smaller value and easier to use wavelength. Otherwise, both of them refer to the same spectrum. Okay, so the spectrum is quite wide. It starts from very low frequencies, like a human voice, goes to very high frequencies, like X-ray, gamma ray, and those radiations. So here is the range of frequencies. The bottom part showing frequencies, the top is showing wavelength. When they are opposite each other, so when the frequency is low, frequency low means the wave changing cycle very slowly. Maybe, for example, 30 hertz here, which is amongst the very low frequency, is 30 times or 30 cycles per second. For example, our electrical signal is 50 Hz or 60 Hz, considered as low frequencies. The voice itself is from 300 Hz to 3 kilohertz. Here, the second part here in this spectrum shown. The first one is extremely low frequency. Second one is voice frequency, which is 300 to 3 kilohertz. Now, if you look at their wavelengths, they are quite large in terms of meter. So they are 10 power of 7, 10 power of 6 meters. So that is wavelength. So then we have very low frequency is below 30 kilohertz. Then we have low frequencies. These are standards, names given by some standard organization, and is a standard across world. Everybody call them usually same names and range of frequencies. So then we have medium frequencies, high frequencies, very high frequencies, ultra high frequencies, I think super high frequencies, extremely high frequencies, and goes more. If you look at here, so then somewhere it comes to millimeter waves, they are now in gigahertz. Then it goes to microwave. Then if you look here, wavelength become getting smaller, and when the frequency become too fast, the waves become very close to each other, then wavelengths become too small. So then it goes to towards the optical spectrum. Here somewhere we call it radio wave, so means we use for radio frequencies. And here somewhere we call it for optical spectrum, which is a start to reach to infrared, which is the lowest frequency. Then it comes to visible, go to ultraviolet. This is going to higher frequencies. Then it goes to X-rays, gamma rays, cosmic rays, and so on. The higher frequency, they are more harmful, and they can travel shorter distance in the way, I mean, in space, because you need more power to transmit them. Lower frequencies can go easier, and they can travel easier with even lower range of, I mean, power. Okay, so that is a spectrum. So okay, so what is frequency? As we mentioned, is the number of cycles of a signal. So I believe all of you are familiar with this because you already know about electrical signals. They have electricity, have usually the power supply in Philippines. I believe you know is, I think, 60 hertz, right? So you should know as an electrical engineer third year, you know what is frequency. So in communication system is the same frequency, of course. So Usually we show them by hertz, the unit, or is 1/second, means how many cycles happen per second. In other unit is hertz. So wavelength, on the other hand, is same thing, but refer to one cycle to see how long is one cycle. You know, when we talk or we produce wave is like a same as the wave you see in water. If you drop something in water, you can see there is wave produced. This wave, they have like up and down, they moving, and they are vibrating on the wave, on the water. So this up and down is in fact wave, everybody knows. So what is wavelength? From one peak to another peak is the wavelength measured by from one peak to another peak, for example. So the length of this wave is referred to wavelength, and the unit is usually meter. Of course, it could be called in micrometer, nanometer, or centimeter. And it shows by lambda. So as you can see here, it shows by lambda. That is wavelength. Depend on the application, either we call sometimes frequency or sometimes we call wavelength. Here it is showing one example. So this is, for example, one cycle. For frequency, let's say if this cycle takes 1 second, the full cycle. So the first one is half a cycle, then is another half a cycle in opposite polarity. So we have positive and negative polarity, then it means one cycle. So if this one cycle takes, for example, 1 second, then we call it 1 hertz. If this one cycle takes half a second, then the frequency is 1/second, means half a second, become 2 hertz, means 2 cycles per second. The wavelength, on the other hand, is from one peak to another peak, or from one point to the same point at the end of the cycle. If you start from 0, then you end by end of the full cycle is 1 wavelength. Then you need to measure how long is this wave. So usually we don't have wave visibly to see. The only one available is water. In water you can see wave. So if the wave is very slow, they are wider, then the length is longer. If they are vibrating quite fast, then the wavelength are shorter. So other electromagnetic waves usually are not visible by human eyes, at least. So that's why we don't have a good imagination of frequency and wavelength, or the wave in electrical or in communication system. At least so far was not possible to see. Maybe in the future we have some special system or camera, we can see them. Okay, so let me I show you a short videos, and you can see them a little bit more clearly by visualization.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
From different aspects.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 124. It's on electromagnetic waves, which are the oscillations that create electromagnetic radiation, and they're important. And so light is electromagnetic radiation, and therefore it's carried in these electromagnetic waves. And does light make it from the sun to the earth? Of course. And so that means that electromagnetic waves can make it through the vacuum of space. But can you hear the sun? No. And that means that the mechanical sound waves aren't able to transfer through space. If they could, scientists have estimated that the sound of the sun would be around 100 decibels. So that's about the sound of a jackhammer a few meters away. So it'd be deafening in sound. So it's a good thing that we don't hear the sun, but it's really important that we see it, that those electromagnetic waves make it here. It keeps us warm. It also allows plants to grow, and so we can survive. And so the electromagnetic spectrum is made up of these electromagnetic waves, and they go from high energy, really high frequency, low wavelength gamma rays, all the way down to long wavelength, low energy radio waves. Remember, you're only seeing a small portion of that. But the one thing these all have in common is that they're made up of electromagnetic waves. Those are transverse waves. Remember, what a transverse wave is one where the oscillations are perpendicular or at 90 degrees to the direction of the movement of the wave. And so it's not only in one dimension, we also have electric fields and magnetic fields that are perpendicular to themselves. And so we have oscillations that are both perpendicular to the direction of motion and the corresponding field. And so they can travel through anything. Electromagnetic waves can travel through medium, like light can move through water, obviously, or radio waves can move through the walls of my house so I can hear the radio, but they can also move through the vacuum of space. And so if we look at electromagnetic waves, remember, as we move towards high energy gamma rays, our wavelength is decreasing, but our frequency is increasing. So radio waves has these really long wavelengths around the size of a building, whereas gamma rays would be more the size of an atom itself. But if we look at how they oscillate, remember the wave is going to move in this direction and the oscillation is going to be perpendicular to that. But adding on top of that, we also have these fields. And so the direction of the wave is going to be, we'll say, from left to right in this dimension. But we're also going to have in the Z dimension, we're going to have these electric fields that oscillate back and forth. And then in the Y, or rather in the X, we're going to have magnetic fields that go back and forth. And so to give you a visual of what they really look like, we have these oscillations in these 2 dimensions, and then the movement is going to be in the 3rd dimension. And that starts to explain why we have things like the right-hand rule when it comes to electricity. And so energy can move from point A to point B in 2 ways. It could move as a particle. We could shoot a particle from A to B. But the other way we can transfer energy is through a wave. We could oscillate, for example, the water here, we could oscillate it back and forth. That would create waves that could move B back and forth. Now that would be a mechanical wave because we physically have to have a medium to transfer the energy from one to another. But electromagnetic waves are not mechanical. That means they could move through the water, they could move through the medium, but they could also move through the vacuum of space. And so did you learn to describe the model of an electromagnetic wave?
Okay, so I have also one more, which is also talking a little bit differently. I think some of the information here also looks quite helpful.
Humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist Heinrich Hertz was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high voltage current was applied to the 2 ends of 2 metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection. However, before Hertz, the brilliant mathematician James Clerk Maxwell had already laid out the foundations for electromagnetic radiation by formulating 4 mathematical equations. However, these equations and the Hertz experiment raised a question. How do electromagnetic fields detach themselves from wires and propagate through a space? More specifically, what we need is a traveling electromagnetic wave and not a fluctuating one. Let's explore this logically. Consider an electric charge, which is moving at a constant speed. The electric field around it is shown. Now, imagine for a fraction of a second, it accelerates. After that, it continues its uniform motion at a higher speed. What we need to understand is the effect of this acceleration on the electric field. The interesting thing is that the information does not travel at an infinite speed. Instead, it travels at the speed of light. Similarly, the information about the sudden variation of velocity of the charge does not get conveyed to the whole electric field region. The field near it knows about it, but the field far away still has no idea that the charge has accelerated and it is still in the old state. Let's separate out these regions with the help of 2 circles. Since the electric field cannot break, the field between these distances must transition. This transition field is known as a kink. The kink moves or radiates outwards at the speed of light. To show the kink animation in a clear way, let's move the camera along with the charge. We can say here that the acceleration of the charge has caused an electromagnetic disturbance or electromagnetic radiation. Based on this understanding, we will be able to understand the most important experiment in the field of antenna technology, the oscillating electric dipole. The interesting fact about this simple oscillating dipole is that it produces electromagnetic radiation in a perfectly sinusoidal manner. Let's see how it is achieved. Before getting into the electromagnetics, let's understand how velocity and acceleration vary in this simple case. It is clear that at both ends, the velocities should be 0, and in the middle, the velocities should be at the maximum. This means that this is a case of continuous acceleration and deceleration. The electric field pattern is drawn here when the chargers are far apart and when the velocity is 0. In order to have a better understanding, let's examine one of the electric field lines. Let's observe the electric field line at t/8. You can see that the electric field line is deformed. The reason for this deformation is simple. This time period is the region with the highest acceleration. As we saw earlier, accelerating or decelerating charges cause kinks in the electric field. In short, the old electric field does not get adjusted to the new field very well. This deformation is continuous since there is continuous acceleration in the charge. When 2 charges meet at the central point, the deformed line also meets there. After that, it detaches and radiates. This radiation travels at the speed of light. If you plot an electric field intensity variation with respect to length, you can see that the radiation we have produced is perfectly sinusoidal in nature. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. Now, let's have a look at how this applies to an antenna. A time-varying voltage is applied to the metal wire as shown. Due to the effect of the voltage, the electrons will be displaced from right to left and create positive and negative charges. With the continuous variation of voltage, the positive and negative charges will shuttle back and forth in the wire. This simple arrangement is known as a dipole antenna. The dipole antenna produces the same radiation as we saw in the previous section. In this case, the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. The same antenna can act as a receiver if the operation of the antenna is reversed. When propagating electromagnetic waves strike the antenna, the oscillating fields of waves create positive and negative charges at the ends of the antenna. The varying charge accumulation means a varying voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. We can note here that for perfect transmission or reception, the length of the antenna should be half of the wavelength. This is the first antenna design criterion for proper reception or transmission. The second most important design criterion is a term called impedance matching. Perfect impedance matching will make sure that the waves are radiated in the most efficient way. When an alternating current passes through a circuit, it faces opposition from the combined effects of resistance, inductance, and capacitance. This combined effect is known as impedance. According to the maximum power transfer theorem, to transfer the maximum amount of power, the load impedance should match with the source impedance. For further understanding, let's take an example of a circuit containing an alternator as a source and a motor, bulb, etc. as a load. In this setup, to achieve maximum power transfer from alternator to the load, the impedance of the load must match with the impedance of the alternator. A similar impedance balance is required in the case of an antenna system. Since an antenna works on high-frequency signals, the impedance of the transmission lines also becomes important. Hence, to achieve maximum power, the impedance of an antenna should match to the impedance of the source and transmission line as well. If the impedances do not match, some portion of the power would be reflected back to the source instead of radiating outwards from the antenna. A free space has an impedance value of 377 ohms. In a parabolic antenna, a waveguide is used as a transmission line, which has a different impedance value from the free space. That's why a feed horn is also included in a parabolic antenna. This way, the impedance of the waveguide is matched with the impedance of the free space so that the EM waves can be received properly.
All right, so we have a equation to convert frequency to wavelength or wavelength to frequency. As we said, electromagnetic waves propagating with the speed of light. So, and that is 300,000 meter per second, or 3 times 10 power of 8. So the wavelength can be calculated by a speed of light in vacuum divided by frequency. So if you know the frequency, you can get the wavelength or vice versa. Here we have one example. What is the wavelength if the frequency is 4 megahertz? So to find the wavelength, we need to divide 3 times 10 power of 8 divided by 4 kilohertz, means 4 times 10 power of 6. So then we get a frequency, a wavelength of 75 meters. So and this is your wavelength. So you imagine if you want to transmit such a frequency of 4 megahertz, you need a large antenna. So that is how you can convert wavelength to frequency. We have another example. So, okay, you already know the equation, and we've given you one example. So this is your turn. So there are A, B, C, and D. So I need 4 volunteers to calculate this. So find the wavelengths for these frequencies: 150 megahertz, 430 megahertz, 8 megahertz, and 750 kilohertz. So I give you few minutes, and that's right. Yes, thank you very much for participating. So let's go number 2 first. I give you 2-3 minutes. Yes, that's right. Okay, let's go for example number 3. So our last example. So who want to participate on this? I give you another few minutes. Yes, that's right. The frequency range just now we were discussing. Here there are few tables showing in fact those frequency ranges. You don't need to remember them, but you should be aware. As a electrical student, and for this subject of communication system, you should be roughly aware which range of frequencies are for what range of application or for what applications. So we have extremely low frequencies. Voice frequencies is something everybody should remember, 300 to 3 kilohertz. So usually we call it the voice frequency bandwidth is about 3 kilohertz. So, but in the practice, in communication systems, for each voice, we allocate 4 kilohertz. It's quite a standard to put 4 kilohertz to make sure there is no overlapping or a little bit of space. We have very low frequency, and so the very low frequency includes the higher end of the human hearing range up to 20 kilohertz. So low frequencies, it goes up to 300 kilohertz. Medium frequencies, 300 to 3000 kilohertz. 3000 kilohertz means 3 megahertz. AM radio is this range, within this range, which is 500 to 1,600 kilohertz or 1.6 megahertz. So these are quite a standard across most of the countries. For example, if you have a radio, AM radio, is a little bit old. Today's, I'm not sure the AM radio is still available. Quite some time I haven't listened to radio, but I only remember FM mostly. So, but AM, if probably you need to search somewhere about 1 megahertz from 500 kilohertz to 1.5 megahertz, somewhere there you can find AM radio. In high frequencies, we have some radios like Voice of America, British Broadcasting, I think Communication, British Broadcasting, I forget the last letter, or maybe it's Communication, but it's BBC's famous one. So those are some of the famous waves. So it's from 3 to 30 megahertz. We have very high frequencies. We call it VHF. So then we have FM radios, which is from 88 to 108, so somewhere there. So you need to search there for radio. Television is this channel 12, 2 to 13 is referred to, I guess, American channels, because this book is American author. So very high frequency is from 30 megahertz to 300 megahertz. Then we have ultra high frequencies, which is also some TV channels are there. Military waves also are there, or communication. 300 to 3000 megahertz. We have microwaves and super high frequencies, 1 to 30 gigahertz. Some of the satellite communication, radars, wireless local area networks, microwave oven also within same group. So extremely high frequency, which is from 30 gig to 300 gigahertz. Also some of the satellite communication, some of the computer data, and also some of the radars. So those are radio frequencies or part of electromagnetic wave. Then it goes to optical spectrum or optical wavelengths or frequencies. When it comes to optical, we usually sometimes we call frequency, but we mostly call in wavelengths. So it's very common in optical, we call it wavelength. In other communication, we call more on frequencies. In optical, there are three main regions of a spectrum. Infrared, which is the lowest frequency. Visible spectrum, which is something we see. Any light we see is invisible. Ultraviolet is a little bit higher frequency. So these three are the main spectrum for optical. So infrared there are a lot of applications for infrared in astronomy, for example, for communication as well. We use for all optical communication is in infrared. So optical fibers, fiber optic communication, all across the world, they use infrared. So which is around in the range of 1550 nanometer, or we call it 1550 nanometer, is the main optical communication signal or wavelength. They call it C-band. So in most new TV remote control, all of you, I believe, have a TV with remote control. There are many other devices with remote control. Most of them use infrared. So they have some LED, which sends some signal to your TV to tell you what keys you're pressing, the channel or the voice you change. It sends some signal using infrared frequencies. And many more. I have one short video for this infrared application.
Here at ANU, and I'm with Ryan and Alec and Lish from ABC Canberra, and we were talking about the colors of light and how we can see more than our eyes and what this means for astronomy.
That's exactly right, Brad. So we're used to seeing the visible spectrum of light, so the rainbow of colors that we can see with our eyes. But of course, we can actually go beyond that to see the full spectrum of possible colors. And we really want that for astronomy because we want to get as much information out of the light that we can. So we can go down the rainbow of colors and just off the end of the red part of the rainbow, and that's called the infrared. Now, we're lucky enough today to have an infrared camera to show us what we look like in infrared light. So what can you see here, Lish? What do we look like in infrared?
We look hot and cold. Cool. Let's say cool. I can see, like, so my face is red, but my glasses are cool. Well, you knew that.
So what we're seeing here is the heat that we're producing. So everything that is warm produces infrared light. And so your glass is actually blocking part of the infrared light. And there are other things that we can use to block infrared light as well. So Ryan, if you want to block yourself here with this space blanket, which is designed to block infrared light, what can you see now on the screen?
Reflection. So I just see, I can't see Ryan, he's completely disappeared, but I know he's there.
Yeah, he's totally gone. So that blocks both infrared and visible light. So now we can look at what it looks like with a plastic bag. And this is just a regular garden bag you can buy. So Ryan, if you block yourself, you can see we block out all the visible light. But what can we see with the infrared camera?
Yeah, I can still see him there.
He's still
even
there.
though you probably can't see him in the camera.
So the infrared light from Ryan has made it through to our infrared camera.
So how does that apply to astronomy?
This is a very useful tool in astronomy because it lets us examine things which would appear blocked to us in other wavelengths. So in space, there are big collections of gas and dust called nebula, and we, with visible light, can't see through these nebula, so we'd have no hope of understanding what's inside. But with infrared light, we can actually probe inside of these things to find the warm dust, which is all swirling around from perhaps new stars and planets being formed. So with infrared light, we can study the formation of new worlds and new stars. And there are lots of astronomers up here at the ANU who work with infrared light to discover just that.
So in your telescope, do you have an infrared light detector?
So you can build cameras specifically designed to detect infrared light. But the crazy thing is with infrared astronomy, you have to be really careful that you're not detecting your telescope itself from being warm or even the atmosphere for being warm. So infrared astronomy is both a very hard thing to do, but a very rewarding thing to do scientifically.